Hello everyone and welcome to the class on probabilistic graphical models. My name is Daphne Kohler and I'm a professor at Stanford University. We here at Stanford are really excited to be able to offer this graduate level Stanford class to anyone, anywhere around the world for free. So what are probabilistic graphical models? Well, it's a bit complicated to explain and we're going to talk about that in an upcoming video, but also throughout the entire class. In this video, I'd like to tell you a little bit about the format of this class. The course is going to be offered over 10 weeks worth of material plus a final examination at the end. The content is going to be conveyed via a set of videos augmented with quizzes to reinforce understanding. In addition, there's going to be a weekly problem set where the problem sets altogether are going to be worth 25% of the score for a total of the 9 problem sets for the 9 weeks worth of content. The problem sets are designed to allow for multiple submissions so that each version of the problem set is going to be a little bit different so that you can resubmit the same problem set a couple times to make sure that you really master the material. In addition, there's going to be a weekly programming assignment, and those programming assignments were selected to reinforce specific concepts that we're studying in the course, but at the same time to reveal the range of applications to which the framework of probabilistic graphical models can be successfully applied. So we're going to have, for example, a problem set on how you use probabilistic graphical models to understand the inheritance of genetically inherited diseases. We're going to have one that shows how you can look at a set of handwritten characters and read what's written there. And we're going to have one that allows you to look at a stream of output from a Kinect sensor that gives you both video and range data and recognize human activities. These 9 programming assignments are each going to be worth 7% of the score for a total of 63%, which gives us 12% left for the final exam. What background do you need for this class? Well, it's going to be really hard to do this class without some understanding of basic probability theory. This doesn't have to be very advanced stuff. We're talking about things like independence and Bayes' rule and just basics of discrete distributions, and we also have a few introductory modules to refresh your memory about these basic concepts. The programming assignments will require that you've had some experience programming before, because this is not a programming class. We don't teach you how to program. And because this class merges ideas from both probability theory and computer science, it's really important you have some background in algorithms and data structures. Recommended but not strictly necessary, and we certainly don't require it and we give you the background as we go, is a little bit of experience perhaps in machine learning, maybe some simple optimization like gradient descent, nothing very sophisticated. And it would be helpful to have some experience programming in MATLAB or Octave, although here also we have some introductory modules that help you learn this programming language if you haven't played around with it before. A few other issues that are worth noting. This class has an honor code. This is the norm also for our local Stanford students when they're taking a Stanford class. The honor code here says that you're allowed to discuss the material, in fact even encouraged to discuss the material with your fellow classmates. You can even ask clarifying questions about the problem sets or the programming assignments, but what you turn in has to be your own work. Furthermore, we request that you do not post either the programming assignments or their solutions anywhere on the web so that future generations of students can do the problem sets and the programming assignments independently as well. A second issue to keep in mind is that of time management. This is a graduate level Stanford class and it's considered a difficult one even at Stanford. A typical Stanford student can easily spend 10 to 15 hours a week on this class, and so we would suggest that you budget at least that amount of time for your own efforts on this class if you don't want to find yourself running out of time when the submission deadline comes around. We've built in a little bit of slack into the submission deadline so that if you don't manage to submit by the original deadline, you have a week's worth of grace period, but then that obviously starts to impinge on the next week's problem sets, so we advise that you don't just keep a backlog of assignments throughout the course, because it'll all end up coming back to bite you in the end. Finally, part of the experience of this class is interacting with your fellow students. So for that purpose, we have the discussion forum, which has proven in other classes to be an invaluable resource for interacting with other students, asking questions, and obtaining a deeper understanding of the material. We're also encouraging you to form study groups. These can be physical study groups with people in the same geographical region, or online study groups where you can just discuss the material with each other. We believe that doing this will give you a much better understanding of the material and will make the course considerably more fun as well. So to summarize, through all these different pieces of the content and the exercises, we think that you'll learn fundamental methods in this area of probabilistic graphical models. You'll also get to see and play around with a range of real-world applications for which these methods have been applied, and hopefully you will leave this class with an understanding of how to take these ideas and use them in your own work in problems that you care about. We look forward to seeing you in this class.
Hello and welcome to the class on probabilistic graphical models. Probabilistic graphical models are a bit of a mouthful, so before we define them, let's first figure out what they might be used for. So one example application, which in fact is the one where probabilistic graphical models, or PGMs as they're called, first made its way into computer science and artificial intelligence, is that of medical diagnosis. Consider a doctor who's faced with a patient. The doctor has a fair amount of information at her disposal when she looks at the patient. Predisposing factors, symptoms, the results of various tests, and from that she's supposed to figure out what diseases the patient might have and what the response to different treatments might be. A very different application where PGMs have also been used is that of image segmentation. Here we might have an image such as this that has thousands or even hundreds of thousands of pixels, and what we'd like to do is we'd like to figure out what each pixel corresponds to. For example, if we break up the image into these fairly larger regions to have less stuff to reason about, we want to figure out which of these corresponds to grass, sky, cow, or horse. What do these two problems have in common? First, they have a very large number of variables that we have to reason about. In the context of the doctor, it's all these predisposing factors, test results, possible diseases, and so on. And in the context of the image segmentation, it's the labels for these different pixels or these larger regions called superpixels. The second thing that these applications have in common is that fundamentally there is going to be significant uncertainty about the right answer, no matter how clever the algorithms that we design. So probabilistic graphical models are a framework for dealing with this kind of application. So let's first understand what each of these words mean in the context of this framework. So first, let's consider the word models. So what is a model? A model is a declarative representation of our understanding of the world. So it is a representation within the computer that captures our understanding of what these variables are and how they interact with each other. And the fact that it's declarative means that the representation stands on its own, which means that we can look into it and make sense of it aside from any algorithm that we might choose to apply on it. So why is that important? It's important because that same representation, that same model can then be used in the context of one algorithm that answers maybe one kind of question, or other algorithms that might answer different kinds of questions, or the same question in more efficient ways, or that make different trade-offs between accuracy and computational cost. The other advantage of having a standalone model is that we can separate out the construction of the model from the algorithms that are used to reason over it. So we can construct methodologies that elicit these models from a human expert, or ones that learn it from historical data using statistical machine learning techniques, or a combination of the two. And once again, the separation between the algorithm and the model and the learning in the model allows us to tackle each of these problems separately. So that was the word model. What about probabilistic? The word probabilistic is in there because these models are designed to help us deal with large amounts of uncertainty. So uncertainty comes in many forms and for many different reasons. So first, it comes because we just have partial knowledge of the state of the world. For example, the doctor doesn't get to measure every symptom or every test result, and she's certainly uncertain about the diseases that the patient has. Uncertainty comes because of noisy observation. So even when we get to observe certain things like blood pressure, those observations are often subject to significant amounts of noise. Uncertainty also comes in because of modeling limitations. So we're going to have phenomena that are just not covered by our model. All sorts of different obscure diseases, for example, that might cause the same set of symptoms. It's impossible for us to write down a model that is so detailed that it includes every possible contingency and every possible factor. And so you're going to have uncertainty and variability that is simply due to modeling limitations. And finally, some people would argue that the world is inherently stochastic. Certainly, if you go down to the quantum level, that's true. But even at a higher level, the modeling limitations of complicated systems are such that one might as well view the world as inherently stochastic. Probability theory is a framework that allows us to deal with uncertainty in ways that are principled and that bring to bear important and valuable tools. So first, probabilistic models provide us, again, this word declarative, a declarative representation that is standalone, where you could look at a probability distribution and it has clear semantics that represent our uncertainty about different states that the world might be in. It also provides us with a toolbox comprising powerful reasoning patterns that include, for example, conditioning on new forms of evidence, or decision-making under uncertainty. And because of the intricate connection between probability theory and statistics, we can bring to bear a range of powerful learning methodologies from statistical learning to allow us to learn these models effectively from historical data, avoiding the need for a human to specify every single aspect of the model by hand. Finally, the word graphical. The word graphical is here from the perspective of computer science, because probabilistic graphical models are a synthesis between ideas from probability theory and statistics and ideas from computer science. And the idea here is to use techniques from computer science, specifically that of graphs, to allow us to represent systems that are very complicated, that involve large numbers of variables. And we've already seen those large number of variables in both of the applications that we use as driving examples, both in the medical example as well as in the image segmentation example. And so in order to capture probability distributions over spaces involving such a large number of factors, we need to have probability distributions over what are called random variables. And so the focus of this class, and what we'll do for most of it, is to think about the world as represented by a set of random variables, x1 up to xn, each of which captures some facet of the world. So one symptom that may be present or absent, or a test result that might have a continuous set of possible values, or a pixel that might have one of several labels. So each of these is a random variable, and our goal is to capture our uncertainty about the possible states of the world in terms of a probability distribution, or what's called a joint distribution, over the possible assignments to the set of random variables. Now, the important thing to realize when looking at this is that even in the simplest case, where each of these is, say, binary valued, which is not often the case, but say for just the sake of argument, if you have n binary valued variables, then this is a distribution over 2 to the n possible states of the world, one for each possible assignment of these n variables. And so we have to deal with objects that are intrinsically exponentially large. And our only way to do that is by exploiting data structures that encode, that use ideas from computer science in this case to exploit the structure and distribution and represent and manipulate it in an effective way. So what are graphical models? Let's look at a couple of very simple examples. So here is a toy Bayesian network, one that will accompany us through much of the first part of this course. A Bayesian network is one of the two main classes of probabilistic graphical models, and it uses a directed graph as the intrinsic representation here. In this case, remember, we had a set of random variables x1 up to xn. The random variables are represented by nodes in the graph. So to take a look at this very simple example, which we'll discuss again later, here we have a situation where we have a student who takes a course and gets a grade in the course. And so that's one of our random variables. We have other random variables that are also related to that. For example, the intelligence of the student in the course, the difficulty of the course, and others that might also be of interest. For example, the quality of the recommendation letter that a student gets in the course, which is dependent on perhaps the student's grade and the score that the student might have received on the SAT. So this is a representation of a probability distribution, in this case over these 5 random variables. And the edges in this graph represent the probabilistic connections between those random variables in a way that is very formal, as we'll define later on. The other main class of probabilistic graphical models is what's called a Markov network, and that uses an undirected graph. And in this case, we have an undirected graph over 4 random variables, A, B, C, and D, and we'll give an example of this type of network maybe a little bit later on. So these were toy examples. Here are some real examples of the same type of framework. So this is a real Bayesian network. It's a network that's actually called CTCS. It's a real medical diagnosis network. It was designed at Stanford University for the purpose of diagnosis of internal diseases. And it has 480 some nodes and a little bit over 900 edges. And it was used for diagnosing internal diseases by physicians here. Another real graphical model, in this case on the Markov network side, is one that's used for the image segmentation task that we talked about before. Here, the random variables represent the labels of pixels or superpixels. So 1 per each superpixel, say, and the edges represent, again, probabilistic relationships between the label of a pixel and the label of an adjacent pixel, since these are likely to be related to each other. So to summarize, the graphical representation gives us an intuitive and compact data structure for capturing these high-dimensional probability distributions. It provides us, at the same time, as we'll see later in the course, a suite of methods for efficient reasoning using general-purpose algorithms that exploit the graphical structure. And because of the way in which the graph structure encodes the parameterization of the probability distribution, we can represent these high-dimensional probability distributions efficiently using a very small number of parameters, which allows us both feasible elicitation by hand from an expert, as well as automatically learning from data. And in both cases, a reduction in the number of parameters is very valuable. This framework is a very general one and has been applied to a very broad range of applications. And I'm not going to list all of the ones on this slide, and there's many others that I could have put on this slide had there been more space. Let me just very briefly mention a few of them on subsequent slides. So we've already discussed the image segmentation. So just to motivate the benefits of the PGM framework in this context, let's look at these 2 images as an example. Here is the original images. This is the division of these images into what I mentioned were called superpixels, which are these sort of slightly larger coherent regions. And this is what you get if you apply a state-of-the-art machine learning framework to individual superpixels separately. So just trying to classify each superpixel separately. And you can see that you get, especially in the case of the cow, a total mess with different superpixels having drastically different labels. You can't even see the cow in this segmented image. Whereas if you construct a probabilistic graphical model that captures the global structure of the scene and the correlations, the probabilistic relationships between these superpixels, you end up with a much more coherent segmentation that captures the structure of the scene beautifully. We've already discussed medical diagnosis as an example. So here is a real-world application. This was something that was fielded on the Microsoft network for helping parents figure out what was wrong with a sick child. And the site was called On Parenting, and parents could enter the primary complaint and then were led through a series of questions that allowed the system to provide a probability distribution over the most likely diagnoses of what was ailing the child. A very different application is one of textual information extraction, where we might have an article from, say, a newspaper, and we'd like to take this unstructured data and convert it into a structured form. We have some representation of the people in the sentences, locations, organizations, and perhaps relationships. So one such task might be to take this kind of sentence and recognize that these two words together form a person, which might not be that hard given the presence of the word Mrs., but this is a little bit harder because green is also a word, and yet we want to identify it as a person. We might want to then infer that this is a location, and perhaps that this is an organization. It turns out that the state-of-the-art methodology for solving this problem is as a probabilistic graphical model, where we have a variable for each word that encodes the label for that word. For example, here we have the beginning of a person unit and an intermediate label for the person unit, and here is another person unit, whereas here in this variable we would like it to label it as a location. But we would like to capture, importantly, the correlations between both adjacent words as well as between non-adjacent words by using this occurrence of the word green to infer that this occurrence of the word green is also a name. A very different example altogether is one that integrates data from multiple sensors. This occurs in many applications. One such is for integrating data related to traffic from both sensors that we might have in the road or on the top of bridges, weather information, incident reports that we might get in some form. We'd like to take all this together and use a model that, as it happens, was learned from data. And that model is then used to predict both current and future road speed, including not only on roads that where we have sensors that measure traffic, but even more interestingly, on roads where traffic wasn't measured. And it turns out that this was a very successful application that was fielded on in several large cities and with very good results. From a totally different application domain, probabilistic graphical models have been used very successfully for discovering new knowledge that we didn't have before. In this case, the application was biological network reconstruction, where a biologist measured protein levels of a diverse set of proteins in different conditions under different perturbations. And from that, they learned the relationships between those proteins and discovered interactions between those proteins where one was controlling another, including ones that were not known before. So let's conclude this introduction with an overview of what we'll learn in the class. So we'll cover three main pieces related to probabilistic graphical models. We'll cover representations of PGMs, including both directed and undirected representations. We'll also talk about higher level structures that allow us to encode more complicated scenarios, including ones that involve temporal structure, as well as ones that involve repeated or relational structure, specifically a class of models called plate models. We'll talk about inference or reasoning using these models, covering both exact reasoning, where exact probabilities are the output, as well as approximate methods that provide a different trade-off regarding accuracy and computation. And we'll also talk about how this class of models can be used for decision-making under uncertainty. And finally, we'll talk about how you might learn these models from historical statistical data. We'll talk about learning both parameters as well as structure of these models automatically, and dealing with both the somewhat simpler scenario where we have complete data, that is, all of the variables are always observed, as well as the more difficult case where some of the variables might not be observed all the time, or perhaps not at all. And that introduces an interesting set of complications, but also a wealth of very exciting applications, as we'll see. So before we get into the details of probabilistic graphical models, we need to talk a little bit about what a probability distribution is, just so we all have a shared vocabulary. So let's start with a very simple example of a joint distribution, one that is going to be extended in examples later on in other parts of the course. And let's start with an example that involves just 3 random variables. This is what I call the student example, and you have a student who can be described in this case by a variable representing his intelligence, and that could be high or low. The student is taking a class. The class might be difficult or not, so this random variable so the random variable I has 2 values, difficulty variable also has 2 values, and then there's the grade that the student gets in the course, and that has 3 values. In this case, we're going to assume A, B, and C. Now here's an example joint distribution over this set of 3 random variables. So this is an example of P of I comma D comma G. It's a joint distribution. And let's think about how many entries are in such a joint distribution. Well, since we have 3 variables and we need to represent the probability of every combination of values for each of these 3 variables, and so we have 2 times 2 times 3 possible combinations for a total of 12 possible values that we need to assign a probability to. So there's 12 total parameters in this probability. And I'm going to introduce a notion of independent parameters, which we're going to talk about later as well. Independent parameters are parameters whose value is not completely determined by the values of other parameters. So in this case, because this thing is a probability distribution, we know that all of the numbers here on the right have to sum to 1. And therefore, if you tell me 11 out of the 12, I know what the 12th is, and so the number of independent parameters is 11. And we'll see that that's a useful notion later on when we start evaluating the relative expressive power of different probability distributions. What are things that we can do with probability distributions? Well, one important thing that we can do is condition the probability distribution on a particular observation. So for example, assume that we observed that the student got an A. And so we have now an assignment to the variable G, which is G1. And that immediately eliminates all possible assignments that are not consistent with my observation. So everything but the G1 observations. Okay? And so that gives me a reduced probability distribution. And so this is an operation that's called reduction. I've taken the probability distribution, I've reduced away stuff that is not consistent with what I observed. Now that by itself doesn't give me a probability distribution, because notice that these numbers no longer sum to 1, because they summed to 1 before I threw out a bunch of stuff. And so in order to get a probability distribution, what I do is I take this normalized measure, an indication. The word measure indicates that it's a form of distribution, but the fact that it's unnormalized means that it doesn't sum to 1, it doesn't normalize to 1. So this unnormalized measure, if we want to turn it into a probability distribution, the obvious thing to do is to normalize it. And so what we're going to do is we're going to take all of these entries, we're going to sum them up, and that's going to give us a number, which in this case is 0.447. And we can now divide each of these by 0.447, and that's going to give us a normalized distribution, which in this case corresponds to the probability of I comma D given G1. So that's a way of taking an unnormalized measure and turning it into a normalized probability distribution. We'll see that this operation is one of the more important ones that we were using throughout the course. Okay, the final operation that I'm going to talk about regarding probability distribution is the operation of marginalization. And that is an operation that takes a probability distribution over a larger subset of variables and produces a probability distribution over a subset of those. So in this case, we have a probability distribution over I and D. And we say we want to marginalize I, which means we're going to basically sum up, we're going to throw away I and going to restrict attention to D. And so what that does is, for example, if I want to compute the probability of D0, I'm going to add up both of the entries that have D0 associated with them, and that's the one corresponding to I0 and the one corresponding to I1. And that's the marginalization of this probability distribution. A critical building block in a lot of what we'll do, both in terms of defining probability distributions and in terms of manipulating them for inference, is the notion of a factor. So let's define what a factor is and the kinds of operations that you can do on factors. So a factor really is a function or a table. It takes a bunch of arguments, in this case, a set of random variables, x1 up to xk, and just like any function, it gives us a value for every assignment to those random variables. So it takes all possible assignments in the cross-product space of x1 up to xk, that is all possible combinations of assignments, and in this case, it gives me a real value for each such combination. And the set of variables x1 up to xk is called the scope of the factor. That is, it's the set of arguments that the factor takes. Let's look at some examples of factors. We've already seen a joint distribution. A joint distribution is a factor. For every combination, for example, here of the variables I, D, and G, it gives me a number. As it happens, this number is a probability. As it happens, it sums to 1. But that doesn't matter. What's important is that for every value of I, D, and G, a combination of values, I get a number. That's why it's a factor. Here's a different factor. An unnormalized measure is a factor also. In this case, we have a factor such as the probability of ID, comma, G1. And notice that in this case, the scope of the factor is actually I and D, because there is no dependence of the factor on the value of the variable G, because the variable G in this case is constant. So this is a factor whose scope is I and D. Finally, a type of factor that we will use extensively is what's called a conditional probability distribution, typically abbreviated CPD. This, as it happens, is a CPD that's written as a table, although that's not necessarily the case. And this is a CPD that gives us the conditional probability of the variable G given I and D. So what does that mean? It means that for every combination of values to the variables I and D, we have a probability distribution over G. So, for example, if I have an intelligent student in a difficult class, which is this last line over here, this tells us that the probability of getting an A is 0.5, a B is 0.3, and a C is 0.2. And as we can see, these numbers sum to 1, as they should, because this is a probability distribution over G for this particular conditioning context. And you can easily verify that this is true for all of the other lines in this table. So this is, again, a particular type of factor, one that satisfies certain constraints, in this case, that each row sums to 1. Now, these are the factors that we're dealing with will not always correspond to probability. So here's an example of a general factor that really doesn't map in any way to probability because the numbers aren't even in the range 0, 1. As we'll see, these kinds of factors are nonetheless useful. This is a factor whose scope is the set of variables A, comma, B. And it still gives me a real valued number for each of those, for each assignment to A and B. Some operations that we're going to do on factors. One of the most common operations is what's called factor product. It's taking two factors, say phi1 and phi2, and multiplying them together. So let's think what that means. Here we have a factor phi1. It has a scope of AB. Phi2 has a scope of BC. And what we're doing is we're kind of like multiplying a function, f of xy times g of yz. You're going to get a function that is of all three arguments, x, y, z. So in this case, we have a factor whose scope is a, b, and c. And if we want to figure out, oops, that didn't come out good. If we want to figure out, for example, the value of the row a1, b1, c1, it's going to come by taking the A1, B1 row from here, the B1, C1 row from here, and multiplying them together. So we're going to get 0.25. So this is effectively taking the functions or the tables and just multiplying them together. Another important operation is factor marginalization. Factor marginalization is very similar to, in fact, identical to the marginalization of probability distributions. So here, except that it doesn't have to be a probability distribution. So for example, if we have a factor here whose scope is A, B, and C, and we want to marginalize out B to get a factor whose scope is AC, what we're going to be doing is, again, taking both possible values of B. In this case, because B is binary, there's only 2 values, and we add them up in order to get the entry for A1, C1, so 0.25 plus 0.08. And the same, all the other rows in this table are computed in exactly the same way from the corresponding rows in the original larger factor. Finally, factor reduction, again, very similar to the context of probability distributions. We want to reduce, for example, to the context C1. So we're going to only focus on the rows that have the value C equals C1. And that's going to give us a reduced factor, which only has C1. And once again, the scope of this factor is AB, because there is no longer any dependence on C. So that's basically the final operation. Now, why factors? It turns out that factors are the fundamental building block in defining these distributions in high-dimensional spaces. That is the way in which we're going to define an exponentially large probability distribution over n random variables is by taking a bunch of little pieces and putting them together by multiplying factors in order to define this high-dimensional probability distributions. It turns out also that the same set of basic operations that we use to define the probability distributions in these high-dimensional spaces are also what we use for manipulating them in order to give us a set of basic inference algorithms.